Alright, welcome back. In a previous video, we were calculating the derivative of z with respect to x for an implicitly defined function. The techniques of the chain rule allow us to simplify the implicit differentiation calculations. So let's say we have a function of the form f of xy is equal to c. Right? That might be something that looks like x squared plus y squared equals c. And our goal is to maybe figure out what's the slope of a tangent line to this circle. Well, we're going to use our chain rule technology to solve this. So implicitly, y is a function of x. Right? When we have this, we have x squared plus f of x squared is equal to c. Right? Sometimes we then try to solve for what f of x is. So now x is a function of x, and f of x is a function of x. So if we take the derivative with respect to x, then what do we get? We have this function, so f, and it's related to x and y. X is related to x, and y is related to x. So we get del f del x times dx dx, that's just 1. And then we get del f del y times dy dx. And if we solve directly, we get that dy dx is equal to negative del f del x divided by del f del y. So that's saying that if we have a circle, x squared plus y squared equals c, then what we do is we look at this equation here, x squared plus y squared, and we write this. Now it's a function of x and a function of y. So we can ask, what is del f del x? Well, that's 2x. What's del f del y? 2y. So the slope of the tangent line, dy dx, at any point on the circle is going to be negative this divided by this, negative 2x over 2y, so negative x over y. So if we're on a circle, so we're on the unit circle, for example, and we are at 1/2 comma root 3 over 2, then the slope of the tangent line there is equal to negative 1/2 over root 3 over 2, so negative 1 over root 3. Hey, that's pretty useful. Alright, so that's what happens if we have a function of 2 variables. What happens if we have a function of 3 variables? Well, in that case, we have something that looks like f of x, y, z is equal to c. We'll go back to that previous equation and use that one in practice. So implicitly, the z is a function of x and y. So if we're going to create a function, we have, we have f, x, y, z. X is a function of x, y is not a function of x, and z is a function of x and y. So we have here f related to x. Well, dy dx is 0 because x and y are not related. And then we have this, del f del z is equal to del z del x. So what do we get? We get that we can solve for del z del x by bringing the del f del x to the right-hand side, dividing by del f del z. Alright, so what does that mean? Here's our example that we had before. If we have x cubed plus y cubed plus z cubed plus 6xyz is equal to 1, then we can look at, remember, we look at this equation here, and we think of that as an equation, that's our capital F. Now we take, what is del f del x? Well, This has an x, so that's good. So that gives me 3x squared. This doesn't have an x, this doesn't have an x, this has an x. 6yz. And del f del y. Oops, we didn't want del f del y, we want del f del z. And so the only things that have z's in it are these two things, 3z squared plus 6xy. And so that's telling us that del z del x is equal to negative this thing, 3x squared plus 6yz, divided by this thing, 3z squared plus 6xy. Let me move out of the way. Whoa! All right, so there we go. That's our formula for del z del x. Much simpler than the last time. All right, talk to you later.